How's it going, guys? Today we're going to be going over Module 6.1, Graphing Cubic Functions, 6.1, Day 1. So, cubic function is going to have the standard form, f of x equals ax cubed plus bx squared plus cx plus d, where a, b, c, and d are all real numbers, and a is the only coefficient that cannot equal 0. The parent function is given by f of x equals x cubed. And what we're going to do now is we're going to complete this table, and we're going to graph what it looks like. So when x is -2, we put that into our parent function. -2 to the third power gives us -8. We put -1 into the parent function. -1 to the third power is -1. We put 0 in there. 0 cubed is 0. We put 1 to the equation, 1 to the third power is 1, and 2 to the third power is 8. So those are our points. We're going to go ahead and put them into our graph. -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. So our parent function will look something like this. So going on, we're going to look at this table, and we're going to analyze the function and complete the table. The tables are complete, but we're going to go over it. So the attributes of the parent function f of x equals x cubed. The domain is all reals. This fancy R means all real numbers, or from all x values from -infinity to +infinity. The range is all real numbers, or all y values from -infinity to +infinity. For all real y values from -infinity to +infinity. The end behavior, as x goes to +infinity, f of x also goes to +infinity. If we go back and look at this graph, we see if we start the origin right here and we start going right, as our x increases, as we're going from the left to right, our x is increasing. We see our y's are also increasing. So we're approaching in y equals infinity as x goes towards infinity. That's why our end behavior as x goes to +infinity is also +infinity for f of x or your y. And when x goes to -infinity, f of x also goes to -infinity. Same thing. If we go ahead and start the origin over here, and we start going towards the left, we see that as our x is decreasing, go from right to left, our x's are decreasing. We see our y's are also decreasing. So that means as we go towards infinity for our x value, our y value will also be -infinity. Zeros of the function, we only have 1, 0, and that's when x equals 0. And where the function f of x is positive, the function f of x is positive when x is greater than 0. All our y values are greater than 0 when x is greater than 0. And where is the function negative? F of x is negative when x is less than 0, or x is negative when y is negative. Or a better way to say it is y is negative when x is negative. Where is the function increasing? This function is increasing throughout the domain. Another way to say that is that it's always increasing. Where is the function decreasing? If it's always increasing, it can't be decreasing, so it never decreases. And is the function even, odd, or neither? It's odd because f of -x equals -f of x. And to expand on that part right here, if we go back to our table, if we do f of -x, so let's say f of -2, f of -2 should equal -f of 2. F of -2 we said is -8. That's going to equal -f of 2. F of 2 we said is 8. So -8 equals -8. We meet the requirement for this function to be odd. Let's keep going. Now the transformations of the graph f of x equals x cubed. So the vertical stretch, our a value tells us that it's a vertical stretch or compression. It also tells us if it's reflecting over the x-axis or not. Our b value is a horizontal stretch or compression. And it also tells us if we're reflecting over the y-axis or not. Our h value our H term is a horizontal translation, left or right, and our K is a vertical translation, up or down. If you pay attention, this is actually extremely similar to our, to the vertex form of a parabola. The vertex form of a parabola is f of x equals a times 1 over b, x minus h all squared plus k. It's the exact same thing. The only thing that changes is that instead of having an exponent of 2, we have an exponent of 3 now. And all the a's, the b, the h, and the k, they all work the exact same on a cubic function as it did with a parabola, or with a square function. So let's keep going. The graph g of x equals x minus 2 cubed. That's going to be a horizontal translation 2 units right. The graph of g of x equals x plus 2 cubed. That's a horizontal translation 2 units left. The graph of g of x equals x cubed plus 2. That's going to be a vertical translation 2 units up. The graph of g of x, x cubed minus 2, is a vertical translation 2 units down. If you pay attention here, remember our h values are always going to be what's inside of the parentheses is being affected by that exponent. That's why the first two are horizontal translations. And remember, it's in the form x minus h. It's in that form. So if it's outside of the parentheses, it's going to be our k. That's why these two are k's and vertical translations. And the first two are horizontal translations because those are our h's. And remember, it's x minus h. So when we say x minus 2, our h is actually only 2. So stretches and compressions. The graph g of x equals 2x cubed is a vertical stretch by a factor of 2. We see our 2 is outside of the parentheses, so it's not really affecting the x's, or it's not being affected by the exponent. It's directly affecting the y, so it's a vertical stretch by a factor of 2. The graph of g of x equals 1/2 x cubed. That is a vertical compression. Can't get this thing to open up. There we go. It's a vertical compression by a factor of 1/2. It's not inside of the parentheses, so it's going to be our a value. So it's a vertical compression by a factor of 1/2. For number 3, we want the graph of g of x equals 1/2 x to the 3rd power. That 1/2 is now actually inside of the parentheses. And remember, our form is 1 over b. So that makes this a horizontal stretch by a factor of 2, because 1 over b is what the form has to be. So whatever's underneath the 1, in this case it's 2, so it's a horizontal stretch by a factor of 2. The graph g of x equals 2x to the 3rd power. This is going to be a horizontal compression by a factor of 1/2. We know it's a horizontal compression since it's inside of the parentheses, it's being affected by the exponent. So that makes it affecting the horizontal, or it makes it affecting, let me repeat that. It makes it that it's affecting the graph horizontally in some way. In this case, it's being multiplied, so it's going to be a horizontal compression by a factor of 1/2, because it has to be 1 over b, and 1 all over 1/2 is the same thing as 2. So it makes it a horizontal compression by a factor of 1/2. So let's keep going to reflections. For number 1, we're told the graph of g of x equals negative x to the 3rd power. That negative is not inside of the parentheses, so it's affecting the y. So that means we're going to have a reflection all over the x-axis. And that's because if you go from a positive y to a negative y, or a negative y to a positive y, you're going to be going about the x-axis. Then graph g of x equals negative x cubed. That's going to be a reflection over the y-axis. That's because the negative is inside of the parentheses. We're affecting the x's. So you go from a positive x to a negative x, you have to go across the y-axis. That's why it's a reflection over the y-axis. So let's go on and do an example. So this table right here tells you your transformation rule, how to do it. And for example 1, we're going to identify the transformations of the graph f of x equals x cubed that produce the graph of the given function. Then graph g of x on the same coordinate plane as the graph f of x by applying the transformations to the reference points 1, -1, 0, 0, and 1, 1. So first thing we're going to do is we're going to figure out what our transformations actually are. So We have this 2 right in the front. That tells me we have a vertical stretch by 2. The next thing I see is that minus x minus 1 inside of the parentheses. Since it has to be in the form x minus h, that tells me it's going to be a horizontal translation to the right by 1 unit. So we're going to be moving to the right by 1 unit. The last thing I see is that minus 1 at the end. That's our k value. Our k is -1. So if our k is -1, that tells me we're going down by one unit. So now we're going to go ahead and we're going to use our transformation rule. Our transformation rule is the bx plus h for our x values and ay plus k for our y values. And we're going to use our reference points, the -1, -1, 0, 0, and 1, 1. We're going to apply them to the bx plus h and ay plus k to give us our g of x points. So the first thing we want to do is bx plus h. So we're going to plug, well, actually, before we do that, let's take a step back. Let's go ahead and actually define what our a, b, h, and k are. In this problem, our a is 2. That's our vertical stretch. Our b, we're not given a b here, so we're not given a b. That means our b is 1. Our h is 1 because it's x minus h, so it's 1. And our k is -1. Our k is what's at the end outside the parentheses. Our k is -1. So now that we defined our a, b, h, and k, now let's go back to the transformation rules and let's try to figure out our new points, our transform points. So we need bx plus h. Our b we said is 1, so it's going to be 1 multiplied by our x value of the point we're transforming. We're transforming the point -1, -1. The x value of that point is -1. And we're going to add h. H is 1. Next, we have ay plus k. We're going to do the same thing with the y value of the reference point. Our a value is 2. Our y we're transforming is -1, and we're adding -1 or subtracting 1. After, so let's go ahead and figure out what those are. 1 times -1 is -1, and -1 plus 1 is 0. And then we have 2 times -1, which is -2. -2 minus 1 is -3. Next, we have the reference point 0, 0. Let's figure that out as well. Our b is still 1. The x value of the point we're transforming is 0. And we're going to add 1 to that, our h. Next, we have ay plus k. Our a is still 2. Our y value we're transforming is 0. And we're going to add k to it, or adding -1, which is the same thing as subtracting 1. Let's figure that out. 1 times 0 for our x value, the g of x. 1 times 0 is 0, plus 1 is 1. So we have 1 right there. And then we have 2 times 0 for our y value. That's 0, minus 1 is -1. Now we have one last reference point to change. That's 1, 1. Our b value is 1. The x value of the reference point we're changing is that 1. So we're multiplying it by 1. And we're going to add our h value, which we defined as 1. Next, we're going to do the same thing with the y value of the parent function, the y value of the reference point of the parent function we're transforming. Our a is still 2. The reference point of the y value we're transforming now is 1, because we're using this point right here, 1, 1. And we're adding k or subtracting 1. Adding -1 is the same thing as just subtracting 1. So let's figure out what this is. 1 times 1 is 1. 1 plus 1 is 2. So our x value of our g of x to this point is 2. And for the y value of our g of x, 2 times 1 is 2. 2 minus 1 is 1. So now we have our new points for g of x. Let's go ahead and actually plot them. So we have the point 0, -3. 1, -1, and 2, 1. Those are our reference points, and that's what we're going to graph. So our graph, so those aren't our reference points, those are our transformed reference points. So this is what our g of x will look like. That's our transform function, our g of x. And that's how you do it, using the transformation rule. So there's example 2 and example 3 next. You guys go ahead and pause the video. try to figure it out, and then I'm going to show the answers afterwards. Just do it the same way that I did it.